Our failed computer technology, why it does not work. We're going to look at this. First, we have millions of unrelated applications. Unrelated in that they do not share any of the information or logic between any of them. We start with our hardware instruction set, a predefined set of actions on numbers. Very limited. It adds, subtracts, multiplies, divides, compares, branches. That's about it. And it's all up to us to determine what those actions are. Our bootstrap, this is the little program that runs. This is an application that runs to load information off your disk and put it into memory and then start the program counter. And this is generally what we consider our operating system that we load. And this operating system runs other applications. So it's running all the time, and it's determining some action through some command that says load this program and run it. And we've started with this and with IBM's GSO operating system, and it really hasn't changed. And then we have the operating itself, which, like I said, loads and runs other applications. It's fixed. We have no control over it. It hasn't changed in 50 years, even though it should. We'll look at that a little bit in our demo. And then our applications. These are a fixed set of instructions. So all of our applications work on one data structure. So we have Word and Excel and AutoCAD and billions of other little applications that do a particular thing on a particular data structure, and then those data structures are not accessible by any other application. We'll look at this. So our loading action by the operating system is predefined and locked. We have no control over this, which we should, a lot more. Our hardware access is predefined, generally by the compiler, and this is very limited. It's saying we will do these things for you, but we will not give you access to them. We will not show you what we did, and this is our technology. And text. The text we put on the screen is predefined and locked. We have no access to it. We cannot use it. We cannot build editors because we have no access to it, and it's a very graphics predefined. We have to use some other, generally, we don't have to, but generally we could do pixel by pixel mapping of our own graphics, but generally we will use someone else's predefined, poorly defined graphics. And our pictures, these are predefined, definitely predefined and locked. So our JPEGs, how do we access those? How do we access PNG? How do we access any of these proprietary structures by our own application? We can use other people's applications, and that, unfortunately, is where we fail because they are fixed. We cannot improve on them. We need to be able to improve on all these technologies. Videos, pictures you take, you don't have access to. You'd like to. Instead of having some application that you have to find to do the things that you want to do with that picture, change the colors or whatever, those are just, you're really not having access to it. Same with videos especially. These are your pictures of your kids, and you have no access to the information that you provide. The operating system and the technologies that we have lock these out from your access. And the information that you create, somebody else says, oh, well, we'll make that proprietary and unshareable. This is our technology. So our failures, technologies that steal your information, literally lock it away from you. Your car, you can't even access your car information. Our compilers have limited use. Basically, we're using, right now, our technology is we use 3 or more compilers for one application because we can't even instruct our computer, our own application, to do something. File sharing, access to remote sites, and all of this requires 3 or 4 or 5, 10 different compilers, different scripting languages. How do we install something? None of this is working. It's all based on craftsmanship. This is software development, is craftsmanship. It's that one programmer decides this is how I'm going to do. So there are no interchangeable parts. Eli Whitney and came up with the idea and said he could do this for the Army, and he failed, but a few years after his death in 1825 they finally produced a system for interchangeable parts, and yet today we have no interchangeable parts. We have stagnant technologies. We will look at this very closely in our demo. Why is it stagnant? Why can't we move forward? Why can't things change? They can't. Once you have a bootstrap, it's fixed forever. Or an operating system, or fonts, or any of these technologies. It's based upon the concept that we cannot change them. And so anything of value by any company is never shared. So you say, oh, we have nothing open. Our concept of our information is name and value with no associated knowledge. This is really what's hurting us. We have a name, okay, X, and a value, 10. What is it? What is 10? What is X? We don't know. But this is how we write every application. This is the way we associate every database and every piece of information that we have in digital form is a name and value information base. Nothing else. No association, no knowledge. We have no units. We don't know what 10 is. We don't know what the name represents. And we have billions of these name value pairs. That's it. And our versions and lifespan, it's down to, I think, to about 18 months or less for any application. They want it changed. So this is our technology. For making money, these are not failures. This is the technology of making money, not of computer science. So we have a 247-year-old technology that cannot be improved. And we have failed dates. Dates are a duration in our current technology, which is stupid. Which is the worst thing. We have 3 versions of our GPS. We have multiple versions of our IP addresses. We have multiple versions of our numbering systems. We have multiple versions of our character sets. And our fonts and graphics and files, our folder and file systems are failures basically because they don't organize our information. So I'm going to look inside these structures in our little demo here, and we'll look at binary structures, what those look like, and how bad and how useless these binary structures are, and do they have to be. And then our computer languages. I have a bunch of scripting languages and computer languages that we want to look at and see if there's anything really of value in any of these computer languages. Our video structures, and basically just our data structures in general. So let's take a look inside some of these structures. This is a live demo of some binary structures, some scripting files, some of our media files, and what they actually look like internally, and why it's so difficult to program. So we'll look at, and all of these are simply the basic fundamental technologies that every application has to have access to, or executable. This is the file that we run. This is what we build. When we build an application, it's an executable of some kind, whether it's emulated or whatever. It's still the same thing. And this is the structure of it. And so I've looked at this before on my previous video, but we'll quickly look at it here. And so I break it down into name, value, pairs. This is our technology. We have a name and a value. So last block size, I'm assuming, is the last block somewhere. And the header size is 4. I'm not sure what that is, and so on. And I define that in one of my CG2 files. And basically it determines that here's the DOS header, which is that first block that we were looking at. And I typed this in from the documentation. So we look at that, and that's our first file. And then we have different tables in this file that are useful to us, and one of them is our import files. And here we're looking at, this is a bouncing ball program I wrote in 9 different languages, and assembler x86 was one of them. And in here I just called things to put a bouncing ball on the screen. Nothing special, just generally one of our first applications we ever write. And in this I called the 3 DLLs, which contains libraries to draw on the screen and to access the screen, and all of these, create a window and begin painting on that window and access the window and things like that. So we have 3 different DLLs, and the reason we cannot move our application anywhere and it's restricted to this piece of hardware is that we're actually not writing programs. We're calling other applications, and that's why all of these subroutines or access or whatever functions that we're calling here are single points of failure. So if any of these other routines that are not mine fail or change or modify something in a way that I'm not aware of, my application will fail. So if this particular DLL, we can look at this last one here, and we can look at DLLs, and it has exports, and so that's this one. And so that one DLL has 900 and some odd programs, functions that are called by other programs. And so I called 5 or 6 of these, but if any of these fail or change or modify or do something that I'm not aware of, or do something that fails, my application fails. And also I'm calling these, and now these are not portable. These are only work on this one operating system, on this one computer, with this particular hardware, with this particular instruction set. And that's why our technology is stagnant. We cannot change. These applications are, these DLLs are probably designed 40, 50 years ago. Most of this logic is 40 or 50 years old. We're dead in the water. We cannot move forward. We cannot change how any of this logic is. Our DLL, our executables themselves are not. And we can look at other binary forms. Our true type fonts are fixed. They have scripts that DLLs are, I won't get into this, but basically are copyrightable, so you can't really use them. They are one-dimensional, so that to me they're of no value whatsoever. I'm going to create a, instead of a program-based, I'll build a data structure-based fonts so that we can share all of our fonts and have access to them, move them to any platform we want. And that's what we want to get to. But we cannot use these fonts directly. Now, these fonts, if we look at these structures, there are thousands of these structures. Just to get to any of the information, all of these are just name value. I have no idea what these values are, and how to get to the glyphs, which is the, anyway, all this information is in here, so nobody can really use this. They don't document this information. We're required to go through their operating system to get to a very fundamental technology, which is draw text on the screen. And this is cruel, because we need access and be able to move this to any machine on the planet. Well, we're not allowed to. And then we have debase files. These are just a simple structure, and this is the control file that I use to access the debase file. Here it has one of my structures, and it has a header file, and it has two different versions. So a version, which is first value, is a 3, then this is a version 3 file, or 7. Well, what happened to 1, 2, 4, 5, and 6? And do we have 9? There's a lot of missing information in any of our technologies. And this one file is only one file. It's not two different files. We should only have the information in here that's required for this one file. So we can look at the output here, and we can look at this as a CG2, which is my format, and it basically takes that binary file, converts it to text, and gives you the same information that was in it. And so it's basically a tagged CSV. So it's comma, 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 comma for each value. I don't need to put quotes. Up here it tells you if this is a number or not. So this is a number. And this is the first address. So that's what we're faced with, is how do other people structure it? What is the meaning and knowledge base between all of this information? And then we have FITS, which is a telescope image file that is basically used for people with telescopes taking images, and generally those are higher resolution. It's basically just a black and white image. So if we look at the values, I converted this to, let me do the first regular format. And so this particular file, this horse head, has two images. So we have table 1 and table 2. I didn't know what they call them. I just called them a table. And then this is the data structure that they pulled in. So if we look at this, these are the name. These are the field names, name value. We don't really know what they are. We can assume what they are, but date, apparently it's fairly obvious. Now, is this month, day, or day, month? So I really don't know when this was taken. That information is not in here. I guarantee you send this to anybody, your guess is as good as mine. And this is our technology. So what I did is I took this file and I put it in normal format, which is just take the value, stick it out there. And I said, well, I want to compress it a little bit. So I compressed it, and I took it down, and I said, okay, let's do a relative. So each next value in a row is relative from the previous value. So the first one doesn't have a previous value, so it's that value. And the next value is minus. I used a plus and minus for a comma. That way I don't have to take up space. And so the original file was 1.6 megabytes, and the zip file was 1 megabyte. And my normal value, which was this file with the values just as they are, and then in my relative value, so that was 4.3 megabytes, and the zip file was 1.2. ASCII characters compress very well. So I got lower than the raw file, but a little bit more, 17% larger than the 1 megabyte zip file. And then my relative file, which is to take the numbers to be relative, which makes the number smaller, which compresses the file, is 1.8 times larger than the original file, but if I compress it, it's 16% less than the zip file. So we're getting some compression. I then took it and I said, can I make it a little smaller with just some trivial applications? And so I went in, counted the number of times the number was used, and then compressed and then replaced those numbers, the ones, the highest occurrences, 40 top or 50 top, with an ABC through some ASCII characters. If we had a larger ASCII character set, we could do a better compression, simply to get it out as text. I don't want to go back to binary, and this is our technology again. Poor character sets, almost non-existent. We're basically using Morse code, basically the same character set that we used in our teletype because of our typewriter, our keyboard. And so every time I turn around, so it's not, can we write better programs? No, we can't write better programs because our base fundamental technology doesn't work. So we'll look at some of our scripting languages. And so what I did is I said, here's some scripting languages. And it basically breaks it down. And so what I want to be able to do, and Jane, in the system that I'm building, we want to look at access to all binary structures, all scripting languages, and that's what we do. And so here, in what I really want to do is I want to be able to take our scripting languages, and we have some script. We want to be able to actually use SQL within our compilers. Our compiler should do SQLs. Since sample.csv is a table, it knows that it's this name value pair knowledge base that we want to get to. So here we'd be able to add an SQL to the compiler, so it's actually doing something, not just adding, subtracting, multiplying, dividing, and comparing. It's actually performing the actions. And these are not subroutines. We want to stay away from functions and documentation. We want to get to where, yes, we know what SQL is. We could come up with other, more natural language syntax if we want, but the SQL statement is the compressed form of access to any table to do anything, which says I can specify what rows I want simply, I can access what columns I want, I can do calculations, I can do a selection, and so on. And that's what the SQL is, all the possible actions that can be performed on a table. We should be able to do that with everything else too. SQL for tables. What if I wanted to get into a DLL? Could I create a language for that? Yes, and so on and so on. So that's where we're going. But I really want to look at technologies. So we have different languages. So we have scripting languages, and basically this breaks it down into words or tokens, if you will, and then this gets pushed into a compiler. In our case, it would be an SQL statement compiler that says go perform this action. That's all these scripts do. We have the DOM model, and it basically breaks it up and gives you your links and your scripts, and these are the styles. And this DOM model, I think, was one of my home pages or something. And basically it basically breaks it down for you and breaks down into scripts. And so it'll break basically I broke them down into functions, but we could do anything. And then our document and our body and so on. I didn't push this out, but we could basically, what we're looking for is creation of a DOM model in the compiler. So we want the compiler to do this for us. So we break it down into a DOM model, which is a structure that you need if you want to write your own browser. which is where we want to get to, so that anybody can. And we want to actually get where the browser is built for us, so everybody can create their own custom browser, which is critical to get rid of. Really, we want the same format. Let's say this dominant. HTML is not the format I would use. It's terrible. But we want one format that basically creates forms, display characteristics for anything. So if we want to write an application, a Windows application or a workstation application, or create our own internet structure. So if this company wanted a proprietary document format, then they could do that, which would be great for security. That way nobody could. Internally, you use your own network, your own structure, but no, you got to use Chrome or something that everybody knows, and it's, anyway. So we could go to much more secure systems if we had access to the information and better structures that were intelligent. So, and we look at JavaScript, and JavaScript's the same way. It basically says, here's a command, function, test ball, open paren, close paren. And what we do is we take these structures and we say, oh, I could go in and find out the name of all the functions, or where a function starts and where it ends, and so on. And that's fairly simple. Or I could go in and find out when a window variable was being referenced, or find all the variables that were being assigned. Here's a variable script that was being assigned, and so I could, and this HTML was being added to. I could find out things that are not necessarily compilable but are informational. So as I'm writing my applications, I could write a billion types of tools to help me in my own work or in anybody else's work. So I could write better validation. I could inject code here wherever I wanted. So anyway, there's a million things we could do with access to our own scripting languages. So here's Cobalt, and it does the same thing. And if we look at this, it's simply an ask for a action, and that's all it's doing, or declaring something, or deriving something. They're all the same. I did 29 different languages. They're all identical, pretty much. So basically I have 29 parsers for each of the languages. And if I look at the source code, get the right thing. Okay, so if I look at the parser itself, this is the parser for Cobalt. And if we look, there's very little that it has to do. And these are the keywords for Cobalt. If I look at C++, it's pretty much the same. It determines the equality capabilities and the Boolean operators and the shift, and then the different types of numbers, and then how comment or quoted strings, whether it's escaped or not, and get the variable as Unicode and get the numbers and what a comment is. And that's pretty much our technology for any of the compilers. So we take this and we can do x86, which there again is the same kind of thing. So on line 15, it's include C:/ so on and so on. So, and these can be modified to any particular language. Like I said, I did 26 or 29 of them, I think. And they're all different, but they all produce the same information. That means that the compiler itself, I only need one, and then I can compile Cobalt or C or C++ or Sharp or Spring or whatever language that we want. So here I have Swift And it's simply the same thing. Break it down into a command. This, I didn't know what it was, so I just called it a label. But anyway, we get this and we break it down, and once we break this down, and this is all through the compiler. Here we look at videos. We're looking at videos, and this thing is is a nightmare. Here I got to go down 1, 2, 3, 4 levels to find out the size of this video. It's 1280 by 720. Here I got to go down into this structure to find out how long it is. This is I made a short video of nothing really, but it was 5.4 seconds. I took this number and divided by this number to get this number. So it's again name value with no knowledge about what these values are in our information structure. So these are really not shareable. And since there are versions on versions, we need the information that this file actually has, and that needs to go in to the file that's associated actually in this type library or this video. We need the structure to actually be put in there. That way there is no versioning. So we take out of everything out of our source code that doesn't need to be there, and we build a better technology. This is where Jane is going. So pretty much it's going to be a namespace type of environment. So so basically all this information will be accessible through one language. We don't have multiple languages, we have one, and that language accesses all the other languages, all the existing languages. As you see, those are easily done. I did 29, I could do another couple hundred. And DOS commands are simply another language, and all the other scripting languages we have. G-code, which is our CNC type of environments. If we look at that one, it's basically takes a very cryptic language, and these are the values, but I basically line 11, what does line 11 say? Okay, it says 10 G90 means convert to absolute coordinates. I wouldn't know that looking at this. So these are all internal values. We really don't want internal values, and there's no reason for it. And so this is what I'm saying. Our technology doesn't work. It's never going to work. We have too many. Everything's crafted to an individual. This individual said, "Oh, I think G20 or G90 means this," for some reason. G20 means set English units inches. This is our technology. This is why information cannot be shared. This is why we have thousands of compilers and scripting languages. And we have no knowledge at all in any of our databases, in any of our structures. I hate databases from the fact that cars and employees and the cars assigned to them, that's never going to change. And yet we have to go through 15 billion tables to figure out what the organization is. That organization should already be in there for us. And this is why applications take forever to write. We should be able to write applications in a few minutes, not man years. We should have knowledge, have the capability to put knowledge. We don't need the knowledge in there if it's overhead for anybody that. This is why I keep saying our technology doesn't work. We have to move off of what we're doing and have functions that are hardware independent, operating system independent, and move to absolute security. and then get you where the owner of the hardware owns the software, has access to the source code, has access to and permits what other people have access to in his information bases. That's why I don't like applications that access my videos. I don't know what you're doing with them. And with the internet, we don't even see what's going on and off our systems. Our televisions are in here. Like I said, I spent 25 years moving information off of systems for mapping systems. 40 different systems, and it's just obnoxious that people can't access their own information. Well, thank you for your time. I know this is rough. I'm trying to get this whole thing should be done in a namespace. So once we do a namespace, which is what I'm actually, all this effort here is just to get some information out there so then I can write a namespace and be confident that I'm getting a cleaner and cleaner convention for naming things. Because when I say mouse, I know what the mouse can do. And if I say monitor, I know what the monitor can do in the hardware. I don't need billions and billions of values just to get to a font, our font libraries, or our video. A video is just pictures, a set of pictures. And if I want to set in, all of this information needs to be knowledgeable, not just this arbitrary craftsmanship of an individual who doesn't have time to overcome the limitations of our technology. Thank you very much.